Welcome back everybody to another video lecture from Miss Semino. In this video we're definitely going to be discussing gas laws. And so one of the biggest objectives is to describe the relationship among temperature, pressure, and volume of gases. So remember, these are the three big factors that were affecting gas pressure. The next objective is to use the thing called the combined gas law to solve problems. So the first thing I want to discuss is this idea about these gas laws are a mathematical representation, and these gas laws will describe how gases behave, and we're using them for predictions. Remember, in science we're always trying to figure out what's going to happen in the future, so we want to be making these predictions. So the amount of change can be calculated with a mathematical equation, and we're going to learn several of these, and I'm hoping that you're going to write these on your periodic table. You don't need to memorize them, but you do need to know how to make these calculations. And so you're going to need to know both the theory and the math behind these in order to successfully answer the questions. So it's always good to know about the people who came up with these ideas. So the first gentleman we're going to talk about is Robert Boyle. He was born into an Irish family. He became interested in medicine and the new science at Galileo and chemistry. He was founder of the influential Royal Society of London, and he wrote extensively on science, philosophy, and theology, but he's probably best well known, at least for me, from this gas law. What Boyle's Law says is that gas pressure is inversely proportional to the volume, so when the temperature is held constant. So here's the equation, P1, V1, and remember P stands for pressure, V stands for volume. It equals P2, V2, and again we're holding the temperature at a constant. And so what he basically said is that if you're increasing one, the other one is going to have to go down. So let's take a look at this in mathematical ways. So if P1 has a value of 1, V1 has a value of 1, and now if I take the pressure over here and I increase it, let's just say to a value of 2, what is my value of V2 going to be now? Well, I'm hoping that you're going to say that V2 has to be equal to 1/2, and that's because those 2's will cancel because this expression needs to be equal to each other. So if I have 2 times 1/2, that is equal to 1, which is still the same thing as on this side of the expression. But the idea here is our volume was 1, and now it's 1/2. So what happened to the volume? It had to decrease. What did we do to the pressure? It was 1, and then it was 2. So as I increase the pressure, my volume decreased. And that's all we're saying here, is that pressure is inversely proportional to the volume. So we can also use graphs to show this, and if you look at the axes here, we can see pressure on this side, and it's being measured in millimeters of mercury. We can see volume over here. So as our pressure goes up, our volume is low, but as our volume is high, our pressure is low. And so it says here that Boyle's Law says the pressure is inverse to the volume, and note that when the volume goes up, the pressure goes down. And so again, I would call this a J-shaped curve, like a reverse J-shaped curve kind of indicates this inverse relationship between the variables. So here's a sample problem that comes from the regular chemistry student's textbook. And so it says a balloon contains 30 liters of helium gas at 103 kPa. What is the volume of helium when the balloon rises to an altitude where the pressure is only 25 kPa? And of course we're keeping the temperature constant. So here we're listing the knowns and the unknowns. So P1 is 103, the volume is 30, and the new pressure that we're looking at for is the 25 kPa. So our unknown is V2. So we're going to use Boyle's Law here. I always like to rearrange the equation before I start plugging the numbers in, but if you like it to do it the other way, that's fine. So I have the equation here. Notice that V2 is what we're looking for. So the way that I'm going to get V2 by itself is I'm going to divide both sides by P2. And that's what they're coming up down here. V2 is equal to V1 over P1 divided by P2. So you just go ahead and you plug in your values and you come out with a volume that is equal to 1.21 times 10 to the second liters. Again, notice that how they're giving the units here in the correct number of sig figs. So the next gas law that we're going to discuss is Charles' gas law, and this is credited to Jacques Charles. He was a French physicist. He was part of a scientific expedition that were able to fly 3 passengers in a balloon. this is how he became interested in gases. And just as on a side note, these balloons were filled with hydrogen gas, so it was a good thing that he was really careful, because if you remember the Hindenburg, it exploded. So let's go ahead and look at this Charles law. And it says a volume of a fixed mass of gas is directly proportional to the Kelvin temperature. So we're talking about volume being directly proportional to temperature when the pressure is held constant. And so then that's how we're getting this equation down here. V1 divided by V2 is equal to V2 divided by T2. And again, V stands for volume, T for temperature. And a good key thing here to note, though, is that notice they're mentioning the temperature is in Kelvin. So sometimes you'll see problems giving you give you the temperature in Celsius. You're going to need to convert them to Kelvin to get the right answer. And voila, here is a slide that helps you do this. So gas law problems involving temperature will always require that the temperature is in Kelvin. Remember that there's no degree sign shown with the Kelvin scale. And the reason for this is that there's no zero, there'll never be a zero volume, since we never have to reach absolute zero. We might have a 0 degree Celsius, and if we have that temperature on the bottom, it's going to make the expression impossible. So here's just a quick refresher. If you have a Celsius degree, you're simply going to add 273 to it to get it into kelvins. So here's another example problem for using Charles' law, and it says a balloon is inflated at room temperature at 24 degrees and it has a volume of 4 liters of gas. The balloon is heated to a temperature of 58. What is the new volume of pressure if pressure remains constant? So just kind of think about this. We're at a certain temperature, we have a certain volume, we increase that temperature. I'm hoping already, remember we talked about knowing the theory and being able to do the mathematical calculations. I'm hoping that you're already being able to make a prediction that as the temperature increases, the volume must increase too, because it's going to increase the speed and make those particles expand outward. But let's go ahead and look at the math for this. So it says list the knowns and the unknowns, so they're doing that here. Again, our unknown is that volume. So here's our expression. And again, I always like to rearrange my equation, and so we're still looking for V2. So in order to get V2 by itself, I'm going to need to multiply both sides by T2. And then these are canceling out. So then this is how we come up with this expression down here where it says V2 is equal to V1 times T2 divided by T1. And so you can kind of see that's what we're getting up here. You just plug and plug those numbers in, and you're going to come out with an answer of 4.46 liters. Again, notice that there's 3 sig figs because there's 3 significant figures in our given here. The next law we're going to talk about is the Gay-Lussac's law, and this is credited to Joseph Louis Gay-Lussac. He was a French chemist and physicist. He was known for his studies on the physical properties of gases. And cool, in 1804, he made a balloon ascensions to study the magnetic forces and observe the composition and temperature of the air at different altitudes. I just think that's crazy that he's just doing these things in 1804. So here's what Gay-Lussac's law looks like. It looks a lot like Charles' law, but instead of volume on the top, we now have pressure. And so it says the pressure and Kelvin temperatures of a gas are directly proportional, meaning again, as one goes up, the other will also go up, provided that the volume remains constant. So then the idea here is, well, how does a pressure cooker affect the time needed to cook food? And there's a little explanation in your textbook, and you can check that out. But if I am increasing the pressure, I am obviously going to increase the temperature, and so that is going to help the food cook faster because it'll be cooking at a higher temperature. And finally we come to the combined gas law, and this is where we're putting Boyle's, Charles, and Gay-Lussac's law all together, and says the combined gas law expresses the relationship between pressure, volume, and temperature of a fixed amount of gas. And so it's P1 V1 divided by V2 equals P2 V2 T2. And so a lot of times kids won't write actually all 4 of these gas laws on their periodic table. They'll just write just this one, because if you know if volume's being held constant, you can kind of just cross out the volume and know that you're working with a Gay-Lussac's problem here. Also, if it says that the temperature is being held constant, you could scratch out the temperatures and know then you're just doing a Boyle's law problem. So here's just a further explanation of that. The combined gas law contains all the other gas laws. If the temperature remains constant, we have Boyle's law. If the pressure remains constant, we have Charles' law. Oh, actually, I finally found a mistake here. So this T1 should be over here, T2. And then if the volume remains constant, then like I mentioned, we have these Gay-Lussac's laws. So remember, you not only need to be able to calculate these, you also need to know and make predictions about what will happen between temperature, pressure, and volume, and also the relationship in the equations. For example, Boyle's law has an inverse relationship, while Charles and Gay-Lussac's have a direct or proportional relationships to them. Good luck!